6G and 5G in India. So I'm going to turn off my camera to save the bandwidth. And yeah, at the end of the session, I'll turn it on. So if there are any queries and discussions, we can have it. And I'll also go ahead and share my screen. So I hope my screen is visible, ma'am.
Yes, sir. Now visible, sir.
Okay, fine. Okay. So I'll start off now. Is that okay?
Yeah, yes, sir, please.
Okay. So good afternoon, everyone. And thank you again, ma'am, for the introduction. Well, the topic which I've chosen to deliver and then discuss with all the participants is the opportunities and challenges in 6G wireless networks. Of course, we all are aware that India will soon be adopting the 5G technology. We have been reliant on the 4G or LTE technology for a very long time, and very soon the spectrum auctions will be done for 5G, and then India should also take over, working with the 5G. In an FDP where the topics are more into AI, machine learning, and so on and so forth, what is this role of 6G wireless networks? Well, that's exactly what I'm here for, to let you know that AI, machine learning, these have spread their wings so much that they have also come into the networks aspect, where the 5G and 6G wireless networks will be heavily reliant on these AI and machine learning techniques. So let me get started with motivation. I don't think we need motivation to really understand this whole concept, but let's anyway try to be motivated. A decade back in 2010, we were really, surprised and really looking forward to all these smartphones. And now here in 2020, 21, 22, we have these smartphones really don't, surprise us anymore. We are looking at various other gadgets, and especially after the pandemic, we've had so many, gadgets which have come in, and they were basically using different AI machine learning techniques. But this is not where the technology stops. What we are envisioning for the next decade, around 2028 and 2030, is technologies like holographic communication, digital twins, mixed reality, which will be a mix of AR and VR, and so on and so forth. So our technology really doesn't stop there. So basically, what the humans are trying to do here is to make the machines smart, so that the system, the network by itself can adapt to the environment or changes in the environment. And after this adaptivity, the system will give us the highest performance with theoretically zero manual intervention. But I still believe there will be manual intervention at certain points, but the aim is to have zero manual intervention, right? So that is the motivation here. So a quick retrospect on this wireless technology. Well, this wireless technology was demonstrated by Marconi in 19th century, and then like any other communication system, it also depends on the information theory, which was constructed by Shannon in 1948. And what we have seen in terms of the generations of wireless is the 1G, which was analog, which was basically the mobile communication for voice, because during that time in the 1980s and the 1990s for India, we were still using the phone to talk to each other. That was voice communication. So phone was really being used for what it was meant for. But then came the digitization, or the digital era, where we wanted to have applications such as SMS, the data services. Therefore, we digitized the entire technology in what is known as the second generation, which around the globe started in 1990s, but for India, it was in the late 1990s. And because of this digitization, we were able to provide many encrypted services and enhanced data services. Of course, our applications were exponentially increasing, and therefore, in the early 21st century, and for India, in somewhere during the end of 2008-9, we adopted what is known as the 3G technology, which is basically represented by the white CDMA. It also has various data services. The most prominent or the key one is the internet access, the video calls, and the mobile television. So this is where really I believe that we moved away from the voice communication, and the entire service became data centric. So currently today we only use the phone for data. We really do not use it for voice communication, right? So again, with the 3G, we were still not really happy with our the technology, because the applications were ever increasing, and therefore we very soon adopted the 4G or the LTE, which is the long-term evolution, and using complex techniques, for example, the multiple input, multiple output antenna technique, the OFDM, which really splits the frequency into different parts, the orthogonal frequency division multiplexing, the all IP or the Internet Protocol, we were able to achieve very high speed mobile data transmission. And currently, India relies a lot on this 4G and LTE system. So we can say overall, for our society, 4G really has done a lot of reshaping in terms of moving away from the voice communication, for which the mobile is really meant for, but we have more of data centric applications these days. So of course, as the generations have moved on, well, our applications are also exponentially increasing. And today, I think we all will agree that the bandwidth that we get from the service providers is not enough for the applications which we have, and therefore the need to go towards 5G. So what is basically this 5G? Well, 5G again marks a distinction from the previous generations. So it moves away from the Internet of Things or the IoT towards what is known as the Internet of Everything or interconnection of everything, which is IoE. So basically, in IoT, we are trying to have an internet connection to a device or a component, and uh, through that we operate the device. Well, with interconnection of everything, it means that wherever we are or wherever the device is, it could be terrestrial on Earth, it could be in the middle of the ocean, it could be in a desert, it could be up flying in a flight. It doesn't matter, wherever you are, you will be connected to the internet. So that is the IoE. So very soon, in my opinion, around another couple of years or so, we would have moved drastically away from IoT towards IoE, and we'll be using this buzzword called interconnection of everything. So 5G is not something really new. In fact, in terms of the research on paper, they started way back in 2013-14, where you could see really good survey articles on 5G technology and the need to move away or advance from 4G technology. But officially, to say, the new radio and the non-standalone was completed in 2017, and this version in the 3GPP was finalized somewhere in 2018, if I'm not mistaken, around March 2018. And now we are aware that 5G is being deployed starting 2020. Many of our Asian countries have already deployed. India will soon be adopting it. Finland is probably one of the first countries to have adopted this, and they've had 5G for over a year now. And therefore, our Indian government is very keen to work with the Finnish government, and they have MOUs on that. And we have many students going to Finland and working in their wireless communication group. So this is one of the first times we can say that India is taking a lead in one of the generations of wireless rather than just being a follower. So with 6G, definitely India will be a leader in that generation, and our government and Honorable Prime Minister has made it very, very clear. So what are the challenging indicators for 5G? Well, this is again a distinction from 4G and 3G and the previous generations. So what we really would get from 5G is gigabit per second of data rate, and this is the user data rate. I'm sure the participants are aware that whatever the service provider provides is not the user data rate, that is the total data rate or bandwidth, and then it gets split into the number of users that the service provider is provisioning. So what we get at the end user, what he or she gets is really a very minuscule bandwidth of what the service provider has. But with 5G, we aim to have gigabit per second of data rate in what is known as the enhanced mobile broadband. We also hope to have what is known as a very low latency or the ultra reliable low latency. Then for a very populated country like ours, We also hope to have 1 million connections per square kilometer. So you can imagine a place like Delhi or Bangalore, where if you go to a market and you have like thousands and thousands of people, this kind of an indicator where you have 1 million connections per square kilometer would really be a blessing. And also we wish to have what is known as the massive machine type communication. This is there on the paper in terms of 5G technology. When it comes to the wireless technology, of course, the MIMO will advance to what is known as massive MIMO, so we'll have many more antennas. Advanced coding and modulation will be used, and in terms of the spectrum, we would move higher in the frequency to what is known as the millimeter wave communication. Uh, so this will be very low wavelength because the frequency is very high. And then you would have the usual non-orthogonal access, ultra-dense networking, so on and so forth. In terms of network technology, it will be software-defined networking. You'll have the mobile edge computation. I'm sure in terms of computer science, we are aware that we are moving away from cloud computing to more towards the edge computing, which gives a freedom to the mobile user or the user equipment to do most of the computations then and there, rather than relying on some remote cloud. Right? So we've done some amount of work in terms of 5G, and that appears in one of our articles in Taylor and Francis in 2022. So I put in the reference here. You can go ahead and see what kind of work we had done. We had done basically some work on deep learning, connecting the neural networks to really see what could be the performance analysis of such a communication in 5G. Before the deployment itself, and I mean large scale deployment, there are already issues in 5G, and these are on paper. Well, of course, these will be a little enhanced once the deployment is complete. And so basically, what has happened is that the mobile broadband has gained more priority than the other parameters like latency and massive machine type communication, which makes sense because we're talking more in terms of the customers, and the customer is really interested in only getting the highest bandwidth. Individually, we are really not interested in the latency part or the massive machine type communication. So already higher priority has been given to this broadband, enhanced mobile broadband. So that is one of the difficulty that the service providers and the industry is facing. The other is when you try to push this IoT scenario towards the interconnection of everything, it becomes it becomes a problem because you have so many applications, for example, vehicles, industrial IoT, so on and so forth, and just having this interconnection of everything with all these applications becomes very, very difficult. So we really do not know as of now how the actual demands in the future would look like. Of course, we know they are increasing exponentially, but we really do not know what they would look like. So therefore, you cannot do a proper prediction out of it. Of course, you can take a data set and do the training and the usual machine learning, but we cannot predict what the actual demands would look like. How would these points or parameters change over the course of period? For example, right now, mobile broadband has more priority, and later we could see that latency would become one of the priorities. So we are not aware of that as well, and we don't know how this entire ecology, how will it evolve. So there are already certain issues which need to be solved in regard to 5G, even though 5G has not been deployed globally as much. This trend basically follows the previous trend, and I would like to give an example here. So we all know that 2G is the best solution for voice communication. However, this was actually proposed in 1G. Similarly, we know that 4G or LTE, which we are using these days, is the best solution for mobile internet. However, this was actually proposed in 3G. So basically, what we have learned from the previous generation is that one generation would propose certain aspects which it wants to aim at and fulfill. However, it will not be able to fulfill that, and the subsequent generation would then take over and then provide solutions to these issues. So if we go with a similar idea and the similar learnings, then it is quite likely that whatever 5G has aimed for, it will not be able to really fulfill all the aims. and therefore its successor, which is the 6G wireless technology, should be in a position to fulfill all those aims. And this provides a huge motivation to move to move towards 6G and already start talking about 6G. And we'll see in a couple of slides that even 6G technology is not something new. It was actually people started talking about it in 2015 and 16, and it really picked up pace somewhere around 2018-19. And now in India, after the pandemic or during it has really picked up pace in terms of research. The 5G, like the previous generations, also depends on the cellular concept, where we assume that there are certain cells, and based on these cells, the handovers will take place, and the users would move in and move out, and so on and so forth. But 5G, what it does is, because it moves from the sub gigahertz, that is where the 4G network really works, towards what is known as the millimeter wave, or a very high frequency, somewhere between 30 gigahertz to 100 gigahertz. And this is known as the new mobile spectrum, and the capacity is really, really high. So the cells here can be really divided into the types based on the application. For example, you can have a macro cell to solve a very huge coverage issue. You could have a pico cell if you want to solve an issue based on, let's say, an enterprise coverage or a street service. And then you have a very small femto cell if you want to solve an issue in terms of home or an office. Right? So based on that, these cells can be divided. But the important aspect is that like the previous wireless generations, the 5G is also dependent on this concept of cells. So it's a cellular communication. Right? Let's look at the trends, and the trends are very, very clear. The market has already defined it. The service providers know it, that now moving from 5G towards 6G would take less than 8 years. In my opinion, the way the research is going, it would take even lesser than 6 years, because there's so much advancement in technology, and with AI and ML coming in, it'll just take it'll just be very, very quick. But compared to the previous generations, you can see on that graph that it almost took a decade and a half to move from 3G towards 4G, and then possibly from 4 to 5G. But that's not going to happen with 5G to 6G. So really, the research in terms of 6G by the academics and the industry is being done timely, and there's lots and lots of articles and white papers from industry. Notably, Samsung is one of the leading you know R&D sector into this, and there are many other industries as well. So what is basically 6G supposed to have? Well, 6G, I would say, would be an extended version of 5G, and that would solve the limitations in 5G in terms of system coverage and internet of everything, or interconnection of everything. So we could be anywhere on this planet, and we will be connected to the internet. That is what 6G would provide to us. Therefore, this is one of the diagrams which I picked up from a white paper by Samsung back in 2020, where they clearly show that if we adopt the 6G, then in terms, as a customer, I should really be very happy, because you can see that the user experience data rate would have increased 10 times. So from zero point 0.1 Gbps, I would get 1 Gbps. In terms of the peak data rate as well, there would be a 10-time increase. If you're more towards the efficiency side, then even then the energy and the spectral efficiency would be 2 times. So in terms of spectral efficiency, for example, I'll be able to transmit twice the amount of bits per second. So that's a good thing, but that would require advanced modulation techniques. In terms of latency, density, and reliability, also there will be huge improvements if we go from 5G towards 6G. But there is an issue. There's no clear description of what 6G is, and that is exactly what the researchers are working on. So this kind of a work has really picked up pace after 2020. It is now rigorously being done with a lot of protocols and a lot of descriptions and architectures coming up. Almost every week you can say that there are articles based on that. So as I was mentioning, that 6G is not something new. It started way back, and these are the two examples which I've picked up. So you can see that in 2016 itself in the United States, the defense research project was sanctioned, and they started working on this very high frequency of 95 gigahertz, 3 terahertz, and this was officially done because it was granted by the FCC. And then similarly in 2017 in the EU, projects were sponsored which were based on 6G innovation. So currently there are online many such projects in different countries, and you can always go online and look at what are the results, what these industry related research are really giving. So the next aspect is in terms of what is the need for 6G, and I think this really does not require any explanation because the graphs speak for themselves. And as consumers, customers, we are well aware that this is exactly what is happening with us every day. So the graph number 2 is really important because I can relate myself to that. It's a traffic volume per subscription. So as a subscriber, I know every month I'm using a lot of data. So every year my data usage is just increasing exponentially because now there's access to so much audio and video and everything. And especially after the pandemic where education was also online, the need for this very high speed internet has really increased. But then there is a problem because 5G, like I mentioned, is a cellular technique. It is also a terrestrial technique like 4G and 3G. Therefore, its coverage is going to be very, very limited. It will have mostly the same issues what 3G and 4G had. So we cannot really expect 100% of the global population to be connected at all times. There are going to be, hitches over that. So to make everything interconnected, well, we need to think in terms of connecting uh, terrestrial, that is Earth, with the sky, with the ocean and the desert. Therefore, we are looking at in terms of channels, let's say connecting a base station or an antenna with an optical fiber which is underwater, with a satellite which is there up in the air, and let's say in a desert, if you want, you could have an optical fiber or a satellite communication. So basically, we are looking at a, a hybrid communication. Until now, we've been working individually, as in people work on optical networks, satellite communication, satellite networks, or wireless networks. But now we'll have to come together and work on these networks. And you can already start envisioning what the issues would be because let's say if I take the example of the usually implemented TCP IP, that will not function now because now the channel, the physical layer has completely changed because it's not just a wireless physical layer or an optical physical layer, it's a hybrid physical layer. Therefore, what would be the interoperability of these physical layers, that needs to be defined by the higher layers, for example the network layer and the application layer. So we need to really design a new protocol, and I will come to that towards the end of this presentation, where this is one of the open research areas where as a computer scientist, I can sit and start thinking if my physical layer consists of these 3 or 4 different channels, then how the network layer or the transport layer should now function, because now the physical layer is just having a different channel with different kind of bandwidth and different demands. So the higher layers will also change, right? So basically, the 6G will solve the issues which will exist in terms of 5G. So that's a motivation why we need to move from 5G towards 6G. So if we compare the 1G to 6G communications, well, I'm not going to compare 1G to 4G because we already know that 4G is going to outperform the previous ones and 5G will outperform 4G and the lesser generations. But if we look at the last 2 columns, that is a comparison of 5G and the 6G, what it's supposed to have, the second row and the third row is eye-catching, where if you see the maximum rate, which is about 35 gigabits per second in 5G, would really increase to 100 gigabits per second in 6G. That's more than twice an increase. Also, if you look in terms of frequency, we'll move from 90 gigahertz towards 10 terahertz. So that's quite an increase in terms of the frequency. Of course, in terms of multiplexing, we'll still remain with the OFDM. In terms of architecture, this is something important. The massive MIMO would be replaced by what is known as intelligent surfaces, more specifically the reconfigurable intelligent surfaces, where we use AI mechanisms to make these surfaces, the antennas themselves, as very smart. So I will be talking about this in one or two slides. And then we'll move from Internet of Things towards Internet of Everything. And really the security and the privacy and the secrecy, these will all take a hit, and newer techniques need to be designed on that. So these are all really open problems in terms of 6G. So this is another very good diagram which I saw in one of the latest articles, which really shows what is the capability of 6G in terms of the previous generations. And you can see on the left hand side of the diagram, it's quite small, but the man who's surfing on the right hand side, the entire area is very, it's quite large, and that shows the capability of 6G. So really what we are expecting from 6G is to have a global virtual existence. The way ITU puts it forth is to have a ubiquitous virtual existence, which basically means everywhere, having a virtual existence everywhere. And whether we like it or not, our society really has moved towards having a virtual existence, especially after the pandemic. So we really need this kind of technology. So what is the proposed architecture of 6G? Well, this is something which I've already highlighted. The one would be that it will be a combination of the space, air, ground, and underwater network. So you'll have, let's say, the wireless technology working with the optical fiber technology and the satellite technology, and this will take care of the ground, underwater, and space networks. So we are looking mostly towards a four-tier network, that is space, air, terrestrial, and underwater. And in this kind of a scenario, it is absolutely not possible to have a cellular architecture. Therefore, what is proposed for 6G is a cell-free communication. So a cell-free communication basically means that the user can be moving anywhere because there is no boundary of cell anymore. And therefore, so to a layman, this is more like there's no concept of SIM card. So I don't need it to store the information, and I'm not going to be on a roaming, for example. I just keep moving, and the base station, the nearest base station, the antenna, is going to decide the best, technology and the network for me. And since this has to be done at a very rapid speed, manual intervention is not possible, and therefore AI and machine learning techniques come into the picture. Therefore, how to allocate these kind of resources, that is how to do this handover, handoff, how to give the best network to the user. All of this needs to be done in a cell-free environment, and therefore the role of machine learning and AI is really important to optimize the allocation of these resources. So let's look at this cell-free communication a little bit in detail. Well, this will be a tight integration of multiple frequencies, and the communication technology will become very heterogeneous. So you're going to have different applications and technologies requiring different bandwidth. The other issue would be the user, as I pointed out, the user will move seamlessly from one network to the another, and there'll be no issues of handover, handoffs, and so on and so forth. So the best network will be automatically selected from whatever is available. So we need to pick up the best AI machine learning algorithms. So currently, with the setting that we have, the user movement, if he moves from one cell to the other, it causes too many handovers, and there are effects such as delays, losses, the ping pong effect. So all of that can be minimized, reduced using a cell-less or a cell-free architecture, and this will also provide a better quality of service. So this kind of a scenario will really take connectivity to a multiple level, and also the hybrid technologies, let's say a multi-tier technology will be used in that case. So this is one of the distinction aspects of 6G when compared to the previous generations. It would be a cell-free communication. So this is one of the proposed architecture of 6G, and I say one of the proposed because there are so many. But the striking aspect in this architecture is the combination of various engineering aspects which really is not present in the previous generations, because the previous generations were standalone. They were only terrestrial bound. Therefore, they were really not communicating with space, underwater, in the ocean or on the desert. They were basically just grounded. They were working only on the ground. Whereas with 6G, you can see left hand corner, there'll be free space optics, where you will be working with a satellite communicating underwater, with the help of optical fibers. But then you could be, let's say, on ground, let's say on a smart home, and then you could work, if you're a patient, for example, then you could work with a doctor who's sitting remotely, which is what we do with Internet of Things. But then this has distance issues. But with Internet of Everything, that issue will also go away. That is the aim of 6G, right? Then there are many such applications in terms of the robotics, automation, then how to integrate the ground with the satellite, and so on and so forth. So there's a whole lot of applications which you can see in this proposed architecture of 6G. And very lately, the aspects of brain computer integration, the BCIs, have taken up, and it requires very advanced techniques in terms of engineering. So 6G really offers all the engineering, I don't want to say departments, but all the engineering aspects to come together and then work so as to provide solutions to specific applications, right? So that will be one of the architectures of 6G. What basically is the vision of 6G? We've already seen it, to provide an intelligent mobile society which is everywhere, ever present globally, and also to meet all these demands by 2030. So, International Telecommunication Union has already put up a deadline of 2030, where we need to really have this 6G. But in my opinion, we'll have it much before that. The research is just mind-boggling, the kind of research which is happening on 6G. So what are the requirements? Well, the first requirement is in terms of coverage, because we need to interconnect everybody everywhere. So the capacity has to be very, very high. Therefore, we will be moving from the millimeter waves, as in 5G, towards what is known as the terahertz region, which is very, very high frequency. And I will touch upon that in the forthcoming slides. And the user data rate will be very, very high, which I've already pointed out. And then the speed of the mobile communication, because the user is not going to be static. So if I want to provide internet connection to vehicular networks, then there are so many issues, because vehicles are just constantly moving. So to provide internet to these kind of vehicles is a real challenge. So the speed of that mobile user is also one of the issues. Uh, it needs to serve the internet of everything, as I've already mentioned. In terms of spectrum, like I was mentioning, we'll move from a sub gigahertz, around 5 to 6 gigahertz frequency used by 4G, to a very high frequency of millimeter waves, that is wavelength, which corresponds to about 100 gigahertz, which is used in 5G, to a very, very high frequency of terahertz, which is 3000 gigahertz. So we're talking about really huge amount of frequency which is available. But then how to use this frequency efficiently? Can we share this kind of frequency? Because no one user requires this kind of bandwidth. So all of this open problems of research. I will also be mentioning the research which my team is working on, and participants who are interested can then collaborate with us. So the requirements of 6G I've already touched upon, and this diagram really shows what would be the requirement of 6G. So you can see you could be indoors, you could be on the road, or you could be in a forest, ocean, desert. It doesn't matter. You'll always be connected with the help of base stations, antennas, through optical fibers, through satellite communication. It doesn't matter. You will always be connected. Therefore, you will have a very broad and very deep coverage. So broad because the globe is just very long, and deep because you also have the deserts and the ocean. So you'll have a broader and a very deeper coverage. So we're looking at something like uh, this particular link, which is an inter-satellite link. It could be an inter-aerial link, an aerial to ground link, a satellite to ground link, and so on and so forth. So we're looking at multiple such links. but because this is not present in the previous generations. We are looking only at the terrestrial to terrestrial link, that is just base station to base station, antenna to antenna on the ground. We are not really talking about having a combination of satellite and wireless networks. We're not doing that in the previous generation, but now that will change, and you have this new scenario, and therefore the protocols and other designs also have to change. More requirements of 6G move from millimeter waves to terahertz towards. Also, there is a lot of research on visible light, which is at much higher frequency. Then, as I was mentioning, how to use this frequency better, how to share it, how to manage it. This is something that my group really works on intensely, and we design algorithms on how the frequency can be shared and allocated properly. Then it comes to the AI technologies, where we are trying to move, as I was mentioning before, from a cloud computing scenario towards an edge computing scenario, because now we cannot depend on a remote cloud to do the computations or store data for us and then accessing that data and the computations from there. Rather, the user equipment, in the case of wireless, it would be the mobile phones or the tablet or the laptop, must be smart enough to do the computations then and there and by themselves, so that latency would also not be an issue. So this is one of the open research areas in terms of personalized intelligent network. The other is because I'm going to be using AI, machine learning, and I'm going to be in this the internet world, the virtual world. The cyberspace security becomes one of the major issues. You also have blockchain, and so such large data, the big data is going to be generated. So managing all of that is also one of the issues. So there's lots and lots of research going on in terms of blockchain and big data when it comes to 6G. Then merging the computation and navigation, this is something which I have already mentioned before. And then, like I was mentioning, the big data, we have the edge computing, AI, blockchain. Also, how to make all this, uh, how to make all these functions dynamic, because the static functions will not work because the customers are on the move all the time. And then lastly on this slide, I want to mention something which is new in terms of what is known as the swarm intelligence. There's a lot of talk about artificial intelligence, but there's also research going on what is known as the swarm intelligence, where instead of making a particular device or a certain component or a small group of components intelligent, in a swarm intelligence scenario, we make an entire network or a huge system smart by itself. So that's why it's known as a swarm intelligence. So it's a collective intelligence, and you're then supposed to get the data, train the system based on this data, and then excuse me, go ahead with making the entire system intelligent. So there's some amount of research which exists on this swarm intelligence as well, and there's some amount of research of this swarm intelligence in regard to wireless networks, which also exists in the literature. So what are the applications of 6G? Well, this is something which is mentioned very clearly in another white paper by Samsung, where it lays out its vision on 6G in terms of what is known as the mobile holograms. So we already know that AR and VR are the key applications of 5G, but with the computations which are really growing exponentially, we can safely say, and the industry agrees too, that holographic communication will be one of the most important applications of 6G. Of course, with this, you have many other applications, for example, the wireless brain computer interactions, the Internet of Bots or Internet of Robots, the drone taxi, so on and so forth. There are just so many applications which are available. So I just want to give a glimpse of these advanced technologies and applications which we are really looking at. So this slide really shows you a glimpse of these advanced applications. For example, the truly immersive mixed reality, which will combine AR and VR and give a mixed reality. The mobile hologram, a digital replica. This is something which a lot of Internet of Things researchers are working on, where you make a replica of the application where you're working at. Then you have the holograms, a zoomed in version of these applications, where you would be really be able to bridge the real and the virtual worlds. So these are some applications which really our society wants to have very soon, and the next generation will definitely be working on these kind of applications. So there's a lot of advanced research on these applications. So each and every application, if you take, is one of the use cases of 6G wireless networks, because the backend of this needs very high bandwidth, which will be provided by the 6G network, and then each of them become a use case or an application of 6G. So overall, what is going to happen with 6G? Well, as I was mentioning early on, this would just become an extended version of 5G, where the mobile broadband would become an enhanced mobile broadband. The low latency would become ultra reliable low latency. The machine type communication will become massive. You'll have ultra reliable, very low latency, 3D communications, and unconventional data communication. So everything what is there proposed in 5G and whatever exists in 5G, where 6G will just become an enhanced version, a bigger version of that, so to say. So that is the vision that the researchers have in terms of 6G. So this is the next part of my presentation. The earlier part till here was all about motivation of why we should start moving towards 6G from the 5G, and then what is the need and what would we really achieve if we moved towards the 6G technology. Well, now I want to focus more on what are the what are the important aspects and the open areas of research that we could have in terms of 6G. So this is where the open areas of research start. And if you're someone who's interested in doing the AI or machine learning for networks or computations, then there are some open problems which I would be stating as we move ahead. Ma'am, before I move here, do I take questions now, or should I do that at the end of the session?
So maybe we'll give participants one chance. Actually, I've
Okay.
muted them. 1 second, I'll turn on their mic so that they can ask.
Okay.
Okay, so participants, your mic is all unmuted. So if you have any queries, please feel free to ask, sir. Any questions? Okay, I think, sir, there's no questions. Maybe we can proceed, sir.
Okay, ma'am. Okay. So I think maybe at the end, once I mention most of these open problems for research, maybe there'll be more queries on that.
Yes, sir.
Okay. So from this slide onwards, I intend to uh, give the open problems of research over various aspects of 6G. And for that, what I've done is, as you can see on that diagram, I have uh, distinguished two parts to 6G, where on the left hand side, you will see that this word new has been bolded, because these are the aspects that which are required absolutely new in 6G. These do not exist. We cannot adopt them from 5G or 4G. Whereas on the right hand side, if you see the word ing has been bolded, that is to mean that these aspects already exist in the previous generations, mostly in 5G, and we only need to do a little bit better than that. For example, if I take the right hand side of the diagram, expanding coverage. So we already would have an expanded coverage in 5G, but we need to expand it further by integrating the terrestrial communication with the satellite and the optical fiber communication. Similarly, there would be an increased system capacity in 5G already, but we need to further increase it in 6G, and therefore we need to have a decellular or a cell-less architecture and a very user-centric UDN, which stands for ultra dense networking. So ultra dense networking UDN is already there in 5G, but we need to make it user centric. And to do that, we need to have, let's say, for example, edge computing, because that will be done on the user's system itself, right? And then similarly, the last point, adding capabilities. So capabilities are already added in the 5G, but with advanced computing and enhanced AI techniques, we would be able to add much more capabilities. As opposed to the right hand side, if you look at the left hand side, it says new resource and utilization method of spectrum. So we cannot adopt the techniques which are there in terms of spectrum in 5G, because we would have moved away from millimeter wave towards terahertz. Therefore, these techniques have to be absolutely new. Therefore, this offers much more open problems of research as opposed to the terms on the right hand side. Similarly, if we are more into the modulation format aspect, then newer modulation formats are required. So I mentioned one of the examples called OAM, orbital angular momentum, and I will be talking about that in one of the slides. And then we need to have a new core network, because the existing networks are two-dimensional, because they work only mostly on terrestrial, but with the integration of fiber and satellite and the terrestrial base stations, now we need to have a 3D architecture, and therefore newer protocols, and therefore newer ways to manage that kind of data and traffic. Right? So this will be the flow of the presentation henceforth, where I'll be talking about these 6 aspects individually. So let's first talk about the coverage issue, and it is already known from basic communication theory. If you want longer coverage at cheapest cost, then satellites are the best. So going by that theory, and this table shows you a comparison of satellite communication with terrestrial communication in terms of mobile technology. And you would see that the satellite communication really outperforms the terrestrial communication. Therefore, it is the best technology to adopt. But the difficulty is to have this technology integrated with the terrestrial communication. But the motivation is that if we are able to do this, then we would achieve a wider coverage at lower cost. So as I've already mentioned, 6G will integrate this mobile communication, which is terrestrial, with satellite communication. And the research right now says that the satellites in the low Earth orbit or the medium Earth orbits can be used for this integrated kind of communication technology. So what is the challenge? To design a new core network architecture and mobility management. Specific challenges will always exist in terms of satellite communication, and that is one in terms of Doppler shift and Doppler variation. So there's a lot of research going on in terms of, if you talk about standalone mobile communication, but with integrated satellite mobile communication, this shift, Doppler shift and variation becomes even more stringent. The next issue is in terms of transmission delay, because we're talking about 6G being ultra low latency. But if you visualize, my signal needs to go from an antenna, which is on the Earth, to a satellite, which is, let's say, a low Earth or medium Earth orbit. From that satellite, if I want higher coverage or larger coverage, then that satellite needs to most likely communicate with another satellite, which will form an inter-satellite link. And then through that next satellite, the signal is sent back to another base station on the Earth somewhere. So you can see that even though this communication could be few milliseconds, but in terms of 6G saying ultra low latency, this is still a large delay. So how to really minimize this kind of delay is an open challenge. And then that is the third point, which I mentioned, how to have a transmission technology for inter-satellite link, because these satellites are going to be far away, right? So the larger the coverage on Earth, the more inter-satellite links would be required, and because of that, the delay is also going to increase. So these are some open challenges when it comes to integrating satellite communication with mobile communication. The next is with something which I had mentioned previously in terms of reconfigurable surfaces. These are known as RIS, Reconfigurable Intelligent Surfaces. There are some researchers who also call it as IRS, which is intelligent reconfigurable surfaces. Anyhow, basically these are nothing but hardware technology to improve the spectrum and energy efficiency, and these artificially reconfigure the environment of the electromagnetic waves, and therefore they become smart. So you can say that these surfaces are can be manipulated in a certain way so that we are able to enhance the performance of the signals by how the reflections of these signals would happen, and then you can get higher gain and bandwidth out of these kind of surfaces, right? So these surfaces are known to provide a good path for propagation where the line of sight really does not exist. There's lots and lots of research going on in terms of RIS or IRS, and one of the references which are provided on this slide. These authors work really rigorously on this, and there's a whole lot of material in terms of reconfigurable surfaces. There are also a lot of research going on in terms of meta surfaces, and therefore that brings me to the next slide where we talk about a meta surface lens. It is basically a phase shifting structure which would be applied to a signal that is radiated from an antenna array. And you can see there would be a baseband processing, uh, beam forming, and then you have chains of radio frequency. You process them, and then through the lens you are able to really direct them to where the receiver is at. So you are able to really adjust the beam direction in when you're using meta surface lenses. There's also talk about using metamaterial antenna, and this is more popular as compared to metasurface lens, at least from what I have read, because the metasurface lenses, if you compare the metamaterial antenna to a metasurface lenses, then really the metamaterial antenna does not require a separate antenna array to uh, have phase shifting done. So that's one of the advantages of this metamaterial antenna, and it acts as a resonant surface or resonant antenna to radiate direct beams itself. Right? So your beam forming is enhanced. You are able to direct the beam much better if you use a metamaterial antenna. So if you're interested in terms of the antenna aspect, and uh, if you can direct your research towards reconfigurable intelligent surfaces. One of my team also works on origami antennas, where we develop our own origami shaped antennas, for example a helical or a square flasher circular antenna, and then we perform do the tests on this. And these antennas are mostly used in satellite applications. You have these box satellites which are proposed by various organizations to be put up near various planets. So in that kind of a satellite, these origami antennas would really work because they are very small and very cheap, and their directivity is very, very good. So if you're interested, you could direct your research towards these antennas. The Of course, the next one would be an advanced version of what is being used in 5G, and that is more of the super massive multiple input, multiple output scenario, where you have more than, let's say, 5 to 10,000 antenna elements which would be deployed, and the advantage that you would get from that is very, very high spectrum efficiency, and this would happen through the technique of spatial multiplexing. You already have very, very high frequency over the frequency axis, but now with having bundles of these antennas together, you in space we are able to increase the capacity by as many number of antennas that we have, and therefore the energy efficiency and the throughput would also increase. And if you use the non-orthogonal multiple access, which will be used in the 5G and 6G technology, then this would really enable this massive MIMO kind of a scenario. Next is the topic on spectrum, and this is something which my team also works on. So I'm sure we are all aware of this spectrum demarcation, where we move from the electronics part towards the photonics range, and we can see that the millimeter wave really is in a very high frequency of somewhere around 30 gigahertz to about 100 gigahertz, and thereafter the terahertz region starts from somewhere around 100 gigahertz, going all the way towards 300 to 400 gigahertz, and we are entering towards the photonic case. So this is a range where we are looking at in terms of various applications where we would move towards, let's say, secure imaging, for example, or X-ray imaging or ultraviolet in medicine, and these are possible applications and scenarios. So when it comes to the spectrum, and there's some amount of work which my group had done in terms of dynamic spectrum assignment technique, and it appears in IIT Journal of Research and Taylor and Francis. So you can have a look at that. It basically talks about how to share the spectrum, this huge spectrum, in a dynamic manner, and can we have the very high frequency or very large spectrum being shared with passive as well as active users. So the study really talks about that. So you could have the terahertz band or the visible light band, which is at even higher frequency than terahertz. So terahertz is somewhere between zero point 0.1 terahertz to about 10 terahertz. This is where the 6G would probably operate. If you want to go higher on that frequency, then you have visible light band between 400 to 800 terahertz. Current research shows that visible light band is good enough for indoor scenarios. For outdoor scenarios at that high frequency, the losses are very high. More specifically, the molecular absorption and the scattering has a major effect on that. When it comes to the terahertz communication, where there are two types of these communications, one is known as the solid state, which is basically based on the frequency mixing mechanism, which we have in an analog modulation technique like the frequency modulation. The other is a spatial direct modulation, where you take the baseband signal and you take a very high frequency carrier and then use the modulator and you get a very high frequency modulated signal. The issue there is, do we have a modulator that really operates at that high frequency? The answer to that is no right now, but there's a lot of research going on. Specifically, researchers have tried to use the material called as graphene, which is shown to operate really good in terms of performance at terahertz frequency. So they're trying to have modulators made up of that material. So terahertz communication would be used for holographic communication, and that's why people want to move from this millimeter wave range towards the terahertz communication. It also has different applications and advantages to it. So next comes the channel modeling and the capacity analysis. And as I mentioned, at high frequency, well, the frequency is very high, therefore theoretically the spectrum would be very high, but that is not so because there are many losses which are available. For example, the absorption, rain attenuation, path loss, penetration loss, there are human blockages, spatial consistency, so on and so forth. Therefore, one of the major challenges is in terms of designing the novel path loss models and thereby designing different power allocation and radio access schemes. So this channel modeling at terahertz frequency is one of the open research problems which many researchers are talking about. The next is, even though the frequency is very, very high, because of the effects, namely absorption, path loss, and so on, the distance of propagation becomes very small because now we cannot transmit the signal for long distance. It will meet many losses. Therefore, that is a trade-off that needs to be addressed. Therefore, you could provide very large data rate, but only for a short distance. So, is that useful for our applications? The answer is no. Therefore, what can be done about it? So, there are newer networks known as nano networks which have come in, where you can split the very large network into smaller networks, and each of them work in tandem with each other, and then they join up to give a good performance to the entire network. So that is something that you can look at. So as I've mentioned, that the effects like diffraction and scattering will already be there in very high frequency, and this has been established by the researchers. Therefore, in terms of or in comparison to the millimeter wave in 5G, the terahertz channel is going to be very sparse, and therefore it offers much challenges when compared to the 5G channel. So there have been certain studies which have shown the transceiver and the hardware designs in terms of for the terahertz wireless radio, and this is one of them, which shows a design at 300 gigahertz, and it for a wireless transceiver chipset using a CMOS chipset. Uh, and basically, what this study also shows, I'm not really showing you the details of the study. The study already exists, but I'm only showing you what were the scope of research from the study. And what the authors really found out was that hardware is a big challenge at high frequency. Uh, Low power hardware circuits is a major challenge. How to make them energy efficient, how to have MIMO systems work with them. Can you have the aspect of nano antennas? How to synchronize the elements of this hardware setup? All of this is a major challenge, and with AI into it, AI already has major challenges in terms of hardware. So this is just going to add to that problem. Next is in terms of what are the other challenges that could exist in terms of spectrum. Well, uh, there are two aspects. One is known as the cognitive radio, and that is one of the most popular kind of techniques in which you have many wireless systems which share the same spectrum, and they use different spectrum sensing techniques and interference management techniques. So, cognitive radio for 5G, 6G communication is a very popular application, and there's a lot of research going on. Recently, a newer trend on cognitive radio has started, which is known as symbiotic radio or SR, which basically gives one more layer of sensing, if you want to call, to the already existing cognitive radio. So here in symbiotic radio, we have multiple subsystems of the same wireless system, and these work together, and you have one more sensing layer to reach to the actual wireless system. So the performance of the entire system increases one more level through this intelligent cooperation. So if you want to work more on the spectrum access technique, spectrum sensing technique, and how to do this in an intelligent manner using different AI and machine learning, then cognitive radio and symbiotic radio is the applications to look at. And there's a lot of open problems on that. So basically, how the AI would be used, I'm slowly coming towards how to use AI and machine learning into the network. So basically, where it would be used is once you make a decision on how to use the spectrum or how to access it, then the major job, if we take the TCP/IP or the OSI layer, for example, then the MAC layer really needs to decide or it needs to have technology through which the collisions could be avoided and how to sense this carrier, and that's where the AI really would work, where sensing of this carrier on the channel would be done automatically rather than the system coming one by one and checking and going back, because we cannot afford that kind of deal, right? So AI really would be one of the blocks in between. If you want to visualize as in terms of the layers, then it would be somewhere between the physical and the MAC layer, and let's say the MAC and the network layer, and it would decide how to access the channel and how to sense the channel. Right? So overall, the industry has already decided, on most notably Samsung, that terahertz will be used as the frequency, and also AI will be one of the most important component when it comes to the spectrum. So we've done some amount of work on this as well, where we were able to do a survey on what are the machine learning algorithms which could be adopted for the 6G techniques, and that work appears as a book chapter in one of the books in IGI Global, so you can have a look at that. So next comes the aspect of modulation format. This is more in terms of the physics, so I'll keep it short. But if anyone is interested, there's a lot of work going on in terms of modulation. So in terms of the electromagnetics, we already are aware that the wireless system is based on the traditional plane, the electric field, magnetic field. But apart from this linear plane, we also have what is known as the angular momentum, the helical plane, And this is where the whole concept of orbital angular momentum comes in, where you could use this helical phase as a new resource to enhance the capacity. Therefore, this OAM has these different modes. And so if you look at the left-hand side of the diagram, you can see different colors, for example, blue, green, and let's say red. And you can see that each of them are orthogonal to each other. So therefore, they are never going to interfere with each other. So these modes are then transmitted over free space. These are then received at the receiver side, and all these modes are spatially overlapped. So since they are orthogonal, they are not going to interfere. So more the number of modes, more is going to be the capacity. Right? So that's the whole idea theoretically. But then there are issues because these modes are going to have phase issues. There is going to be the transceiver is not going to be aligned properly, and that will lead to phase sensitive issues. Beam divergence is one of the issues which already exists, and that how would you transmit these modes? So these are some of the aspects. So I'm keeping it this part a little short because I don't know how many participants would be more into the modulation format, but if any of you are, then this is one of the newer advanced modulation techniques to look at. So overall, with OAM, right now the research community has identified that you could have a very high order spatial multiplexing, and this may not be achieved by the MIMO technology. Therefore, one could move towards OAM, but this research is still ongoing. So next is the aspect of how to increase the system capacity. Well, we have touched upon this previously in regard to how not to have a cell, and then how to have a user-centric, ultra dense network. So we cannot have a cell structure where we just keep splitting the cell over and over again, which basically is some idea from the research community. But then by doing this, you approach the limit of the system. Therefore, it is best to not have a cell architecture, and that is exactly what is going to happen in 6G. So you will not going to talk about cells at all. And in terms of the ultra dense network, well, we need to see how the density of the access points and how the density of the users match. There should not be an imbalance there. And in terms of frequency, there's going to be the terahertz region. Well, what are the challenges? One would be what would be the architecture, because now we do not have a cell. Once we do not have a cell, the mobility of the customer or the user is not in our hands. Therefore, the mobility will be a factor. Once mobility is not a factor and the users are moving all over the place, what would be the interference? To what extent can we tolerate the interference and how it can be repaired? That's a major issue. And then once all of this is happening, how do we allocate the resources? How do we allocate the spectrum, the power, and other resources required by the users? And then with all of this, what would be the security and privacy? So each of these issues are novel in themselves when it comes to the 6G technology. So anyone could pick any of these issues, and really it is more of a doctorate level work, each of these issues. Then next is to add the capability in terms of computing and AI. Well, we have discussed some part of it. Now I'll be going into the detail of it. So what we need to have in 6G is what is known as the 3C network, which is more of user centralized, content centralized, and data centralized. So we're really not talking about voice here, because we have understood that data is going to really be the major factor in the next generation of wireless as well. So everything is going to be data and content centralized, and then the user who is going to require or going to support this kind of data, right? So AI really becomes one of the most important aspects to meet these requirements, because the applications are massive and the performance has to be significantly improved. So, what are the challenges? Well, I'm sure if you're from the computer science background, you already must be aware that mobile edge computing is not that simple, because to have that kind of a storage and that kind of a computing on a user device is very difficult. If you want to have a terminal edge, that is computation in between the cloud and edge, that again is not really an easy task. So there are challenges in terms of computation and intelligence if you want to do it collaboratively. The other issue with AI is the hardware by itself. And then can you really have a convergence of all of this in a dynamic fashion? That again is one of the issues. The next aspect is in terms of how the edge computing and cloud computing can be or must be done in 5G and 6G. This is something I've touched upon, and that diagram really shows what is happening there. So the user really is going to become more centric in 6G compared to 5G and 4G. In 5G, you can still see that there is user equipment which is connected in the network, and he or she has some decision to make, but that was not really present in terms of 4G, but this will become more in 6G. And then you could also do what is known as split computing, which is another really good research topic where mobile devices can achieve really high performance by extending the battery life. And this relates to the aspect of wireless energy transfer, which I will be talking about towards the end of the presentation. We have done some amount of work on wireless energy transfer as well. Right. So basically, with the split computing, the the device will be able to give away or send very high computation tasks to resources which are available in the network, and thereby offload most of such kind of tasks. Right? So split computing is also something that the research community is looking at. So next is the idea of AI for resource allocation. In networks, basically the resource would mean frequency and power or energy. So here we are talking about bandwidth and power. So we could use the supervised or the unsupervised learning. But the problem with the wireless networks is, again, like in any AI machine learning domain, the data is the issue, because once you have good data, only then you can train the system and predict and so on and so forth. So data is one of the issues, but the supervised and unsupervised learning can definitely be used. Uh, we have done some work in terms of deep learning, because our work was basically uh, was based on classification. So DL is one of the techniques known to be used for classification or regression. But then there were some issues in terms of performance, but not in our study, but in general. So we could use DL as well. Then comes the aspect of reinforcement learning, where mostly in wireless networks you would use a Q learning technique, but there's a problem with Q learning that as the data keeps increasing, the table also enlarges and the storage becomes one of the issues. This is also one of the algorithms which a lot of studies have used. And the next aspect is in terms of deep reinforcement learning, which combines the deep learning and the reinforcement learning. So I'll also show you the work which we have done very recently, but this is something which we have taken from a study in IEEE Access in 2020, and the same study shows this kind of a diagram where you can see that the services and applications on the top of different industrial IoT applications, for example, or a video stream services, are really governed or monitored by the AI system on the right hand side. And you can see how the resource allocation is done through that AI. So based on those services and applications, there's a feedback which goes from the AI block on the right hand side, and then that feedback moves towards the physical infrastructure on the left hand side bottom. And based on this, now the entire infrastructure or the architecture will adjust or adapt itself. So that is the whole idea of using the various AI or machine learning algorithms in wireless networks. So this is one of the study which I had mentioned at the start, where we had done some amount of channel estimation uh, for uh, for fully connected neural networks using the deep learning. So here we really addressed how to allocate suitable resources in a wireless network, and we got good performance out of our study. We looked at the greedy algorithm, the auction theory, and the game theory, and these are still the most proposed of the resource allocation algorithms or the problems. And we looked at the heterogeneous structure and the high quality of service requirements. Uh, we did not really touch upon this aspect, but this is something which we are currently working on how to have radio resources of in terms of power spectrum and time in a joint optimization, because the optimization techniques, if you consider all these, would turn out to be a very hard problem to solve, and we then need to design heuristics. But then once we design the heuristics, the solution which we obtain is basically approximate. So there's a trade-off going from the actual optimization technique towards the heuristic technique. So what we looked at was really the rapid response in terms of accurate environment modeling. So we designed a mathematical model which could measure the resources in a very complex environment. And then we also looked at the aspect of self-adaptivity, so that the entire system, in our case, the network, is able to adapt itself based on the different scenarios in the environment, and then the resource allocation was actually done properly. So the current work which we are doing, which is under review, and I cannot really reveal much about this work right as of now, but really it deals with the reinforcement learning, which is based on channel assignment, which is dynamic. So we've designed an algorithm based on that, and we're talking about there in terms of channel interference and traffic distributions, stochastic distributions, and time varying traffic patterns and so on. And what we have found is that these algorithms, as I was mentioning, these are hard to solve, and these really become the NP hard problems. And then therefore we need to formulate and propose heuristic methods which would not jointly solve these issues, but do them step by step or in a split format. But the solutions which we obtain from that is approximate. So therefore there's a trade-off over there. So this is, I'm just sharing a glimpse of this. As I mentioned, I cannot share the complete details because the article is still under review. But this gives an idea of what we were able to do using the reinforcement learning, that is the QLEAR. So next comes the idea of machine learning for radio access. So previously we spoke about how to allocate. Now we'll talk about how to access this technology. So there are different kinds of multiple radio technology. And so you could have the time frequency based channel division technology, such that time division, duplexing, OFDM, you have NOMA, hybrid NOMA, OFDM, so on and so forth. These are all existing. And then you have the SM-MIMO, which basically is an intelligent multiple access to 6G network. And this is based on channel state information, or in AI machine learning, what are known as agents. So depending on these agents, we would get the results, and the agent which gets the highest reward, or the reward function for which agent is really high, we tend to use that agent again and again. So different algorithms can be used. Most notably, the ant colony optimization could be used, where your ant works as an agent, and then the ant which really gets most of the rewards is the one that is used a lot. So these channel estimation and signal detection would improve the spectrum utilization and detection accuracy. I'm not going into the details. This involves a complex mathematics, and only those who would be working towards these channel estimations would be doing those mathematics. But algorithms can be done by the computer scientists in terms of various optimization techniques, which can be used to access the to do the multiple radio access. So what must be kept in mind is the high mobility of the users, because the Doppler spread is going to be there at high frequency, and this is going to lead to channel fading. So overall, what we have seen is that how to schedule this access in 6G networks, and that to do this in an intelligent manner that is really an immediate challenge, and that is something which we are really working on. So we want to propose some AI or I would say machine learning algorithms which would be intelligent, so that the access of this radio channel becomes really efficient, and therefore the performance of the wireless network would really increase. So the next aspect in terms of radio access would be the configuration challenge. That is how to intelligently allocate the resources with low latency. Beamforming will always be a challenge uh, because now we have the massive MIMO technology, and this high dynamic communication has to take place. So conventional beamforming uh, can be used at millimeter wave, but it is not intelligent and it does not adapt to a changing environment. Therefore, better kind of techniques are required at the terahertz frequency for the 6G network. And the white paper, which I have mentioned as the reference at the bottom, is something which really talks about how to have these intelligent beamforming techniques when it comes to radio access technology in 6G. So next is about the 3D architecture. Well, again, here this is something which I have dealt with in detail. So in the past, we have had the 2D network architectures, that is terrestrial mobile system and satellite mobile system are standalone or independent. But now we need to integrate them. So as I mentioned before, the medium Earth or the low Earth orbits satellites would be used, and then combine them, have them together, do the computation, navigation, and all other technologies together, and then bring about a global virtual, technology based on that. So, what are the challenges? Well, first is to establish this architecture, and next is how to manage the mobility, and then how would the resource utilization, again by resource I mean the spectrum and the power, how would this be done efficiently? And then this is the last point is something which I had mentioned early on in terms of protocol interoperability. So the same, let's say TCP/IP is not going to work because now we have different kinds of channels which are now functioning together at the physical layer. So a newer uh, interoperable protocol is required in this scenario. So now I'm going to touch upon a couple of, or three to be precise, use cases of 6G wireless networks. There are many more, but we don't have time to really touch upon uh, many use cases. I've already spoken a little bit about holographic communication, digital replica, digital twins. Uh, so in addition to those, we also have the optical wireless communication, because now we are going to be integrating the wireless technology with the optical communication. So if any of the participants is from the optical communication background, you would know that the fiber gives very high bandwidth in terms of terahertz, and it is basically because it is a fiber strand and it is not affected by electrical interference. You can use it, underneath the ground, and it can also be used in the submarine kind of communication, underwater communication. Right? So when you wish to have a terrestrial and an underwater communication, the best solution would be to have a wireless technology with the optical fiber technology, which would connect the terrestrial and the underwater network. So the conventional wireless communication is based on the EM wave, but it cannot provide high-speed data. And like I said, the fiber would be able to do that because the source is predominantly laser, and at high frequency, this laser can emit light at for long distances. So you can achieve very high data rate using the optical fiber. In indoor scenarios, specific fibers called as multimode fibers can be used, which are really efficient to give very high data rates within, let's say, a kilometer or a kilometer half and a half of distances. So one can also opt for visible light communication (VLC), but as I mentioned it before, current research shows that this is good enough only for indoor scenarios. But a lot of research on VLC for outdoor communication is also being conducted currently. The next is in terms of quantum communication. There is a lot of research on quantum communication, especially in Southeast Asian countries. India is also taking a lead in quantum communication. So basically, what we do here is to encode in quantum state. We use photons and quantum particles by superimposing them both on the bits into a what is known as a qubit. Right? So you have 0 and 1 over there. So therefore, it looks more like a clone, and without tampering, you can just send this qubit, and then this is received appropriately. That is in theory. So provides high security. It improves the data rate due to superposition of the qubits. That is the nature. And the branches of quantum communication is quantum key distribution (QKD). This is something which a lot of researchers are working on. Quantum teleportation, I have not seen much research on that, but that could be mostly only because of my reading. But QKD is something which I've seen a lot of researchers work on. And then comes the idea of wireless information and energy transfer. So, in one of our latest articles, which is available on RCIV, we've done a survey on WIET and its related applications in 6G, specifically in the Internet of Nano Things (IoT). So, basically, what WIET is that it is a promising technology to increase the lifetime of battery, that is to charge a wireless system. So the wireless through energy harvesting will be able to the wireless equipment can charge itself. That's the whole idea of WIAT. So it basically uses the same electromagnetic fields and waves as the wireless communication system. It could use sensors and smartphones which will be charged by using this wireless transfer during communication. So the idea is, or the aim is in 6G to have devices without batteries to be supported, and then this seamless integration of wireless information and energy transfer. So you can have a look at our survey article, and you can see what are the applications which we have really mentioned in terms of WIET for 6G. It's freely available for reading over RCIV. So I've also mentioned the link over there. So overall, we've now come towards the end of the presentation in terms of the applications of 6G and what are the open problems. So overall, if we see what are the design considerations and technologies in 6G, you can see that the applications are numerous in number. So if you take, let's say, for example, the massive machine type communication, it will be a smart city or a smart home. If you take a very low latency kind of a scenario, then you are talking about fully automated driving system or industrial internet. If you're talking about any enhanced mobile broadband, then we are looking at applications such as haptic internet, tactile internet, AR, VR, or a combination of those, and holographic verticals, right? And the objectives are pretty known. They have to give a data rate higher than 1 TB, and the techniques to be used could be numerous. So this is a bracket which we are looking at, and then what are the design principles that one can use to really implement those ideas. So there's a lot of permutation and combination shown through those arrows, and this I've adopted from a study in IEEE Vehicular Technology magazine published in 2019, and this is a very good article to really understand what are the considerations and what could be the methods and techniques to be used if you are working on a particular application. So lastly, what is the roadmap and suggestion for 6G? Well, ITO has already specified it completed the 5G standardization in 2020, and that is when a few countries started adopting 5G. And what it mentioned at that time was that the research on the subsequent generation, which is now known as 6G, on next generation wireless technology, should be completed in the period 2024 to 2026, and the deployment should start by 2030. But my study says it would happen much before. Probably in a couple of years, this research on 6G would be really be on the completion stage, and the deployment should start very very soon. So that is the vision of the ITU, and that is the suggestion which they have given. So, in terms of summary of the research opportunities in 6G, well, one could work on the channel model and resource allocation. The channel modeling will be more on the mathematical aspects. The resource allocation is something which my team also works on, where we design different algorithms on how to appropriately take this very large amount of spectrum which is available, and then how to efficiently use it, access it, sense it, and then also we are now working about the management of this spectrum. The new radio multiplexing technologies, where multiplexing techniques are already existing, but then how to have them together is something that one can look at. Like I was mentioning, the new spectrum efficient spectrum allocation is something which we are working on. So there's an article which is under review, which talks about machine learning enabled dynamic spectrum access for 6G networks. So here we have tried to use machine learning algorithms, uh, most notably the reinforcement learning algorithm, to access the spectrum in a dynamic manner. The other points that one can look at is the energy saving mechanisms, which would include energy harvesting. Hardware implementation is possible if you have an industry collaboration with that amount of fund to purchase the hardware and then do the experimentation on that. AI by itself will be a research opportunity, because which mechanism to use and how to use would be a factor. The If you're more on the network economics aspect, then you could work on the capital and the operational expenditures and how to reduce them in a particular network. Application specific improvements, these could depend on different parameters. For example, if you want to work on the bit error rate, the signal to noise ratio, latency, and different such aspects, then you could also look at that. And lastly, something which one of my groups is looking at is known as semantic communications. Well, this is something which is already existing, but not for wireless networks. And so we were able to design a survey article on semantic communications for intelligent wireless networks, where we basically talk about the fact that instead of communicating only the data, that is, if we communicate, let's say, ABCD, and the only job we have at the receiver is to reproduce that ABCD, rather than doing that, if I'm only able to transmit the meaning of the data and the receiver really understands it, then that will save a lot of bandwidth for the wireless technology. So we're not talking about the mechanism of reproducing the data on which many of the systems are based right now. That is known as syntactic communication, where you just reproduce the data as it is, whereas we are talking here more of semantic communication, which is more of the meaning or the context of the data, which is how our human life is based on, because we are deductive learners. So we understand through our experiences, and we learn through that, and we take action. So if our wireless networks are also able to do that, then we'll be able to save a lot in terms of bandwidth, and also a lot in terms of energy. So this is also on RCIF, and it's under review right now, but it's freely available for reading on the RCIF platform. So you can go ahead and have a look at that, and see what are the applications when it comes to semantic communications for wireless networks. So in conclusion, 6G should provide a very high capability compared to 5G. It should integrate the different networks, that is satellite, fiber, and wireless networks. It should be able to integrate the computing, navigating, and different AI technologies. And overall, it should be able to provide us with a good virtual experience, which is what is required by our society. And this should be done before 2030, as per IT. So you can subscribe to my YouTube channel, where I talk a lot about 6G, various videos on 6G. I've also started putting a few videos on semantic communication, and apart from that, I also post a lot of videos in terms of general research. That is how to write an article. The latest video of mine on that talks about what are the common errors that one makes while writing an article, and also how one can publish in very high impact and high quartile journals. You can also connect with me on LinkedIn over that link. So I'm always up for collaboration. I work predominantly on wireless networks. Previously, I've also worked on optical networks on the spectrum issues. So I worked on what is known as the elastic optical networks, which has, as the name suggests, the frequency can be elongated or suppressed based on the need. And then I also worked on space division multiplexing for optical networks, which enhances the capacity of the fibers. And I moved to wireless network domain in the last couple of years. So any of these domains, including the antenna, I'm always up for collaboration. So uh, you can contact me over the LinkedIn. Also, I'll go back to my initial slide, and you can also contact me over the email. You can also connect with me on ResearchGate. I think, yeah, the link is mentioned at the bottom there. So that is all from my side. So I'll now remove the slide, and if there are any questions and interaction, I'll be happy to take it. Thank you.
Okay, that was really a very wonderful session, sir. So we'll open the dais for a Q&A. So participants, if you have any queries, please unmute and ask.